Hi everyone, welcome to our webinar Carbonate Formation Evaluation. I am Abdullah Abdurrahman, Reservoir Business Developer in Reservoir Solutions. I would like to start with just a 5 minutes presentation about Reservoir Solutions and our upcoming workshop. Reservoir Solutions is a company specialized in providing technical studies and courses for oil and gas companies and professionals. The company incorporates many professionals with diverse technical background related to oil and gas exploration and production. Our services include technical reservoir studies, field development planning, reservoir static and dynamic modeling, economic feasibility studies, technical support for academic researchers like PhD and master degrees. We are assisting in writing technical papers and publishing. We have technical petroleum courses by industry experts, and we are providing mentorship programs. For our upcoming workshop, it will be integrated formation evaluation. It will be about 2 weeks workshop with hands-on software to do interpretation for the basic interpretation for well logs and also for the advanced logs like the spectroscopy and the NMR. Okay, this workshop it will be about 8 sessions. Each session it will be about 3 hours per day, and we will have many data sets to be shared with the participants to have application and software. For details about this workshop, you will have into the Zoom chat. We will send a link to register for this workshop into the Zoom chat and also the details about the workshop. Our instructor for today webinar is Dr. Osama. Dr. Osama is a consultant petrophysicist with about 15 years experience in clastic and carbonate formation evaluation. He has experience in using advanced tools for processing and formation evaluation like NMR, acoustic logs, and spectroscopy and borehole image. For webinar rules, so if you have any question, you can drop it into the Zoom chat or uh, please mute your camera and your mic. In case that you wanted to have a certificate for attendance, you can fill into the form that will be sent into the Zoom chat. Join our Telegram channel for the upcoming webinars and courses, and the link it will be sent into the Zoom chat. You can contact us via the mail and the WhatsApp. So thank you all. Hope you nice learning time. So Dr. Osama, you can start.
You see my screen now?
Yes.
Okay. So today our webinar, it will be about carbonate formation evaluation from the petrophysical point of view. We can start by 1 second. Yes. We can start by comparison between the clastic reservoirs and carbonate reservoirs for formation evaluation. When you are working with clastic reservoirs, always the challenges that you are facing in the petrophysical evaluation for the clastics include different mineralogy, include grain size, include texture. So when you are doing a rock typing, you are doing a formation evaluation, you will see that the lithophysis is the main control that control your permeability. For example, you are talking about a delta fishes for sandstone. It will have something called mouse pores. These fishes will have a good permeability. When you are talking, for example, about Levy deposits, you will have a very bad fishes. It will have a very low permeability and low porosity. So you can predict from your lithophysis the poroperm relation based on the texture of the rock and the grain size. But the carbonate reservoirs are different story. They depend on depositional settings and they depend also in diagenetic setting. For example, you have poor connectivity, fracturing, degree of dolomitization can affect your reservoir. Sometimes you are working with a limestone and this limestone, it's a tight, but in some areas it will be dolomitized and after it will be dolomitized, it will have a good reservoir quality. So we are dealing here with something called rock fabric features. It is the differences in the pore size, either from the grain size and sorting, and also the nature and size of vuggy porosity and the fracture porosity. For example, you have a reservoir with interparticle porosity or intercrystalline as homogeneous carbonate, or you have a reservoir with different porosity type, like for example, interparticle, intercrystalline, vuggy, isolated, fractured in the same reservoir. So the challenge for carbonate reservoir is much bigger compared with the clastic. We can see from this layout for Cretaceous carbonate in the Middle East, we have the triple combo, the gamma ray, the resistivity, the density neutron. We can see we have a blocky pattern, same pattern of gamma ray, low resistivity indicating water-bearing carbonate, seeing the neutron density, small variation, for example, here and here, but the main density neutron have the same trend. So if you are using the triple combo alone, for your formation evaluation, you are going to say that I have a clean body carbonate. It's a uniform. It seems that it doesn't have a porosity variation. It seems here it's a water bearing, yes, but it will not be heterogeneous from the triple combo alone. In the clastics, you can work with triple combo alone. But for carbonate formation evaluation, triple combo alone is not sufficient for any petrophysical evaluation. Introducing one of the advanced tools, which is called NMR, nuclear magnetic resonance. Here it's called a T2 distribution. The T2 distribution obtained after acquisition and the processing of the magnets that we are using in this tool. So the T2 distribution is always presented in time scale. This time scale, for example, here from 0.3 to 6,000. As this time scale increase or high value, it indicates a larger pore size, but this condition is only applicable if you have a water-bearing reservoir, because the NMR depend on three processes, something called surface relaxation, bulk relaxation, and diffusion relaxation. So if you have a water-bearing reservoir, the bulk relaxation and diffusion relaxation will not have effect on your T2 distribution. So the T2 distribution here will reflect your pore size, if you have a big pores or if you have a small pores. So the big pores will have a bigger time in the T2 distribution, while the small pores will have a small time in the T2 distribution. So we can see here that here we have a body with a lower time compared to this body. So from triple combo, we can see it's a homogeneous, but in the introduction of advanced tool like NMR provided more solutions for your reservoir formation evaluation. Someone is asking, we can't hear anything. Is my voice is clear? Hello? Hello? Oh, you hear clear. So I will answer the questions in the end of the session. Don't worry. Everyone is hearing me clear, right? Oh, okay. Maybe some people have some problems. Okay, let's continue. So here the NMR-T2 distribution provided more answers that the triple combo will not provide us. From my experience, I worked for like 5 years with carbonate reservoirs. NMR should be acquired at least 2 times or 3 times in your field. It will provide a lot of answers. So moving to this slide, it indicates the challenges that you are going to face when you are doing a carbonate petrophysical evaluation. You need to understand the carbonate in your field. Does this carbonate has microporosity? Is it laminated? Does it have low salinity or high salinity? Because I saw before a carbonate reservoir with salinity 200 K. So the resistivity was 1 ohm and it was producing oil with water cut 0%. So you need to know the salinity of your reservoir because it will affect your resistivity. Multimodal porosity. Does your carbonate have different pore size? For example, at the same depth, you can have microporosity with megapores or macropores. This will have a significant impact on your interpretation. So you need to understand the pore size distribution and the pore throat. You can know something like multimodal porosity by mercury injection from the special core analysis and from the NMR distribution. High capillary, if you have a reservoir with a lot of micropores, it will provide a high capillary water. So you can produce even with a saturation up to 60%. So you need to take care of that. You need to understand your reservoir. Does my reservoir have a lot of capillary water? If that yes, so you can produce up to 60% water saturation. Conductive minerals. One of the most famous conductive minerals are pyrite and siderite. Pyrite iron sulfide and siderite FeCO3. It's iron carbonate mineral. Both of them are present in some carbonates. You need to take care of that. So have, for example, you will know that you have a conductive minerals spectroscopy tool. Spectroscopy tool will provide you that if you have a pyrite and siderite from the volumes that obtained from the spectroscopy, you will do a correction equation to correct your resistivity, not your saturation. And I use this equation a lot by integration of the spectroscopy with my triple combo. Fractures. Fractures is a different story. You need to have an acoustics tool and you need to have a borehole image tool. Connected and isolated Vugs. Also, you need to have acoustics and sonic. If you have a micrite limestone, it will also be challenging because you are going to have a low resistivity bicarbonate. So this scheme is your carbonate evaluation workflow. If you want to obtain the porosity, you need to have density neutron for every well in your field, sonic also for every well. It's not like Clastic. Here, sonic play a vital role in the porosity computation because the acoustic tool will provide you with the primary porosity. The density neutron will provide you with the total porosity. So the difference between the porosity from density neutron and sonic will provide you a secondary porosity. And you need to know if you have a lot of secondary porosity in your reservoirs or not. If you are interested in lithology, and lithology is also has a great challenge in the carbonate, sometimes you have anhydride cementation in your calcite. You have a limestone, but with anhydride cementation. In this situation, you have a challenge. The grain density you are using in your formation evaluation. So how you are going to obtain the anhydride volume? Either by using cross plots, integrating the density neutron and PEF, but what if you have an oil-based mud and your PEF is not reading good? The solution here is spectroscopy, either from different companies like GemTool, like laser scanner from Schlumberger. They are going to provide you with accurate grain density and they are going to provide you with the anhydride volume. This anhydride volume, you will see it and you will correct your grain density that will be used for your interpretation. Then, for example, you need to know the porosity type and the porosity distribution in your reservoir. You can't know it from the triple combo. The borehole image, the NMR, the sonic and scene section integration of these four acquisitions will provide you with the porosity type and will provide you with the pore size distribution. I also forget to mention that the NMR provide a LISO-independent porosity, a porosity that doesn't depend on lithology. It's not affected by the matrix, but the density and the neutron sometimes the porosity are affected by the matrix and the clay. Then moving also, if you are interested in rock typing for carbonate, you need to have a whole core analysis. You need to have a density neutron also and NMR and sonic, because the NMR can provide a permeability, but don't forget that the permeability of NMR needs some corrections, need to be integrated with core. It can be used for qualitative analysis, but for quantitative interpretation, it needs to be calibrated with the core. Then the fluid type. The fluid type in the carbonate, you can't rely on resistivity only. You need to have a sigma to have a cased wall saturation. You need to have a 3D, 4D NMR, the fluid typing mapping. And this is very important because it can differentiate if you have heavy oil, light oil, water, or gas. And the fluid type from NMR are widely used now, especially in the carbonates. and also the dielectric. The dielectric can provide you with the saturation of the flushed zone. And you are going to see in one of the slides, the dielectric are going to provide us the M and N if you have a water-bearing reservoir. So when you are talking about carbonate characterization, you need to put in your mind the Dunham classification. The Dunham classification classify your reservoir. If you have a mud stone, it indicates that most of the reservoir are mud support, only grains with 10%. Wax stone, more than 10% grains, but the most dominant are mud. While pack stone, the most dominant are grains, but there are some muds. While the greenstone, the most dominant are grains and it lake the mud. And also there are bound stone and crystalline. Why you need to know that? Because if you are going to do a carbonate rock typing, you need to integrate the microfiches that are going to obtain from the thin section with the poroperm relation. For clastic reservoir, you can do a poroperm relation with the fishes. For example, you have a massive sand, cross-bedding sand, lenticular sand. You can do a poroperm for each lithophysis. But for carbonate, you are going to do the poroperm relation for each microfiches. And I'm going to show to you at the end of the slides a poroperm relation for different microfiches. We can see here we have a different thin sections with different texture. From the left, we can see we have anhydrite cementation, we have dolomite with some intercrystalline porosity. Here, the anhydrite cementation destroyed your reservoir, it filled your pores, so you need to have a thin section in your reservoir. Here, it's another story. It's a compacted dolomite with some fracture porosity. We can see here, texture is much different than here. So here is going to provide you a different poroperm compared with here. While here we have a big crystals of dolomite with late stage of dolomitization destroying your porosity, but there are some isolated intracrystalline pores. And here we have a different features. It's a micrite with some grain stones. So you need to integrate these thin sections in your reservoirs. For any heterogeneity carbonate reservoir, you need to acquire a CT scan. CT scan, you are going to take the core and provide a CT on it to see if it's homogeneous or heterogeneous. And also you need to acquire a thin section and borehole image. Why? Because if you have a secondary porosity, big vugs, something like this is a secondary porosity and it's a big pore. You are not going to predict this big pore without using thin section, CT scan, and borehole image. This is the shape of big vugs from your image. So how you are going to determine that you have a large pores, something like big vugs, you need to acquire from logs image, NMR sonic, while from the laboratory, thin section analysis, CT scanning, and mercury injection. So what is the use of using whole core analysis? And what is the use of conventional core? The whole core, every 1 feet, you are going to do the permeability and the porosity in these 1 feet, in the entire core. Every 1 feet, you are going to measure the permeability and the porosity. For the block, you are going to take one block from this one, and you are going to measure the permeability and the porosity. If you are dealing with heterogeneous carbonate, the porosity from here will be different from the porosity from the block. So you can estimate the secondary porosity from the core data by using the porosity of the whole core with the porosity of the block. Moving to the Vuggy characterization. If you know that your reservoirs are Vuggy, you can't rely on the triple combo alone. You need to acquire thin sections from the core in 2 or 3 wells, and you need to acquire in the remaining wells borehole images. Okay? Because borehole images can provide you from the different in the resistivity contrast between the vugs. For example, if you acquire a resistivity borehole image, the vugs will appear conductive. Why the vugs will appear conductive? Because if your vugs is filled with oil, for example, this oil will be invaded by the water, and the water bismuth will invade the oil, and you are going to fill the vugs. And the borehole image, its vertical resolution and depth of investigation. Depth of investigation is very shallow, and the vertical resolution is very good. So what you are going to do, you are going to see a circles of black spots. These black spots can be your vugs, but you have a challenge. If these vugs are filled with clay, they will also appear black because they are conductive. And if these vugs are filled with water, which is the water invaded your oil, they will also appear black. And if your vugs, if your reservoir are water bearing, these vugs also will appear black. So you need to integrate the image with the triple combo here. If your resistivity is low, so your vugs will be either clay or water. But if your resistivity have a good separation and it's high, and you see the vugs are black, this indicates that you have a good Vuggy reservoir. By the way, this is the shape of classification. It appears as a big vux, something like that. This is from actual data. So after discussing some secondary porosity characterization, we need to discuss the characterization of the primary porosity. If your reservoir doesn't have any vuggy or fractures or fenesters, any secondary porosity, and you need to do a poroperm, it will be much easier compared with a secondary porosity reservoir. Why? Just you are going to do something called rock fabric number from Lucia 2003. You are going to plot your perm and pore in the core data, and you are going to predict for each carbonate body you have the rock fabric number. And in the uncored well, you know that this body is correlatable with the other well. So you are going to use the same rock fabric number, and you are going to estimate the permeability from your primary porosity that you can derive from the nutrient density. This is an actual example of a bed fishes carbonate. When your points go to here, it indicates that you are class 3. Class 3 suggests that you have, for example, a mud stone or wax stone. But if your points will be here, it will indicate a class 2. But if your points is here, it will indicate class 1. So as your points go from here to here, it indicates class 3, which is bad reservoir quality compared with the class 1. Then we can talk now about fracture characterization. I see that a lot of questions. I am going to answer all the questions in the end of the session. Don't worry. Anyone have questions, he can write, no problem. So natural fractures. The fractured carbonate, it's present in a lot of carbonates in the entire world, especially in the Middle East. The fractured carbonate, you need to acquire borehole image. From the borehole image, you can get a useful information. Like if your fracture is cemented, what it means cemented? It's closed, like it's full of calcite cement, it's full of dolomite cement, it's full of quartz cement. So how you can know it? If you have a water-based mud in your well, so the resistivity image, if it have a high resistive image, that indicate it's something cement, something have a strong resistivity, high resistivity. So it will appear something like that white color. But if you have a water-based mud, well, and you acquire a resistivity image, and this one is a conductive fractures, and you have your resistivity from the triple combo is high, this indicate a good reservoir quality because we can see it's a big fracture with a big aperture here. But there are other challenges. There are some fractures are called bed-bound fractures. They don't appear in the entire borehole image. They appear as a sinusoid. Here and here, not complete sinusoid, sorry, but here it's appear a complete sinusoid. So what is the difference between this and this? The productivity. This one will produce, yes, oil, but it will have a production profile weaker compared with this one. This one can have a bigger production profile. It can stay for a longer time compared with this because this bed band fracture have a small aperture we can see here, and it will be weaker in a reservoir compared with this one. I did some criteria from the well logs from my experience. You can determine by using this criteria the fractures from the triple combo. This is based from my experience because I worked in a different carbonate reservoirs in a different countries. I always find that you will have the shape of the washout. You will have the caliber value is very high compared with the bed size. And you will have a strong resistivity separation. And the density especially, it will be very low and it will go to left to like something like that. And when the density will be very low, it will indicate a good aperture, by the way, from my experience. So when you have a density look like that, This density look like the density of the washout, but it's not washout. So when you see the density like that, you see a resistivity separation. You see a high washout reading between the caliber and bit size. And also, if you have the sonic, even the compressional slowness alone, you will see something called cycle skipping. Cycle skipping, it looks like, for example, you have your slowness value, it's from 40 to 240, and it's carbonate. You will see your slowness will be like that in the carbonate. It will be like 140. And this is not correct for any carbonate reservoirs. But what is the value is very high? The value will be very high because of something called cycle skipping. The slowness should be arrived of the compressional slowness should be arrived at a specific time during the processing, but it arrived later. It arrived during the shear time, not the compressional time, which means you have fractures because the fractures attenuate the sonic waves. They attenuated. They will make it move with a weak velocity. So it will have a high slowness. We can see here, we can also determine the fractures with using something called acoustic anisotropy. If you acquire acoustic tools, you can require from the surface company that I want to, for example, to do something called dipole anisotropy. The idea of the dipole anisotropy, we measure the shear slowness in two directions, X and Y. After we measure the two shear slowness in X and Y, we do some processing. And after we do some processing, we can see the waveform of the shear in the slow direction and the shear slowness in the fast direction. The blue one is the shear slowness in the slow direction. The red one is the shear slowness in the fast direction. When you have a separation like that, this separation is called homogeneous anisotropic, which means you have a homogeneous carbonate, but with anisotropy. This anisotropy suggests that you have intrinsic anisotropy, which is fractures. There is other types of anisotropy. It's called stress-induced anisotropy. It doesn't have this shape. The waveform looks like a different pattern. But when you see this dispersion plot, you see this shape and you have your lobes, you expect that you have fractures from the anisotropy. Another method for fracture characterization is using the Stoneley wave. The Stoneley wave, it's the wave, a borehole wave. It moves along the borehole. When you have something like fractures, the wave will be strongly attenuated. They will go here and they will go here and will be strongly attenuated. But if you don't have fractures, the borehole mode will not be attenuated. So here you have your Stoneley wave and here you have the Stoneley slowness. The Stoneley slowness here and the Stoneley slowness here will be different. For example, the Stoneley slowness here will be higher because you have a fractures. So a method called Stoneley fracture analysis, you can request also from the surface company. They are going to provide you based on the reflection coefficient and the transmission coefficient that happen to the Stoneley. They can predict if you have fractures or not. And you can predict also from the Stoneley if your fractures are open or closed. How you can know it? This layout will be provided by the surface company. You are going to compare the Stoneley slowness, the measured itself after the processing, and there is a Stoneley slowness after modeled inside this model of the Stoneley fracture analysis. If there is a difference between these two curves and you have a good reflection coefficient and the transmission coefficient, that indicates that you have a fractures. And also you can see it in the wave pattern. You have a chevron pattern. Chevron pattern look like that. If you have this pattern, it indicates that you have a fractures in your reservoir without using borehole image. Then there is another slide. You can determine the fracture aperture and the fracture porosity from the borehole image. You can use an advanced methods like fracture aperture computation, and you can you can quantify your reservoir quality of this fractured carbonate. For example, when you have this color, it indicates a low fracture aperture. But when you have a high blue color, it indicates a big aperture. So we can go to this plot by BUS 2011. We can see that as the fracture density increase, here we have a high fracture density. What it means, the fracture density? It means how many fractures per 1 feet. So we have a lot of fractures here per 1 feet. So we have high fracture density. So we can go to high fracture density. But if this porosity from the triple combo is high or low, we can see there are a lot of intervals that the porosity itself is low. So using fracture density with low porosity, so you will be categorized here. So when you go here, it will be categorized like weak to moderate reservoir quality. But what if you have a good porosity and you have a high fracture density? You will be categorized here. So when you are going to be categorized here, it will indicate a high reservoir quality for your fractures. Some other challenges are the electrical properties of the rock. I think everyone know about the A and M and N that are used in Archie equation. The M especially has huge impact in your formation evaluation in carbonate. You can't use the default value, which is 2. It's a different story in the carbonate. You need to know your texture. For example, here we have a molded porosity with interparticle porosity. So here these molds with interparticle porosity, the M is always depend on something called tertosity, or the path of the electrical current in your rock. If the path is directly like that, so the M will be equal to. But if the path of the electrical current will take a lot of tortuous paths, the M will increase, something like that. Let's go from here. You will see it need to move through the pores, and then it will face a matrix. It will try to go to these pores, and then to these pores, and then to here. So you can see here we have a more tortuous path here compared with here. So the M should increase, but the fractures provide a faster path even compared with the interparticle and intercrystalline porosity. So for example, the path will be like that. So here even it's less tortuous than here. So for example, let me draw it here in a correct way. Yes, it will be like that. So here the M will be lower than 2, the M here equal 2, and the M here will equal higher than 2. So how you can know your M? By special core analysis. So you need to acquire special core analysis in your reservoir to know the M value. But you are not going to acquire special core in every well. So you are going to do the rock fabric fishes for each body, predict its M by using the next methods. Let me go here and then we go back to the previous slide. If you don't have a core data and you have a water-bearing carbonate, you can go to this water-bearing carbonate and use this equation, M equal negative log FRF equal to R naught, which is the resistivity in the water-bearing here, over the RW. And you know your RW from the salinity. So you are going to use R naught, which is the deep resistivity here, over RW from the salinity over log porosity. So you can estimate your M here and use it for the other reservoirs. You can use some cross plots. I use these cross plots. If you have a sonic, you can determine the porosity, the secondary porosity, and this secondary porosity with the total porosity. You will go here, for example, we have a total porosity 10%, and we have isolated pores like Vuggy from the image, and we estimate the secondary porosity which was 5. Let me go here. Sorry, let me go here. Anyone, do you hear me? My voice is clear? Just to check. My voice is clear? Okay. So you go here from the porosity 10% total porosity. For example, you have a 4.8 isolated pores from the difference between the neutron density and sonic. You can go here. You are going to do that every depth. Every depth. So after you do that, you can estimate your cementation exponent. You can estimate your cementation exponent at every depth. Then there is other method. It's dielectric tool, and it's used widely in the Middle East. This dielectric tool is very good tool. It can provide you by method called interfacial polarization. This interfacial polarization based on the measurement of the amplitude, the attenuation and the phase from this dielectric tool. It provides you an equation. This equation you can estimate M. If you know your N, the N will be equal M, and you know your frequency, You know, it provides you also with a water-bearing porosity, and you know the saturation of the fluxed zone from the other method, which is called electronic polarization. So you can compute the M based on the dielectric at each depth. Let me get back to the previous slide. Here we have two actual cases with different M. Here, I remember that the operator computed the saturation based on the M equal 2. But when it provided to me to do a revise for this interpretation, I do a borehole image and I found that we have isolated vugs. The saturation here, when you're using M equal to around 30%. 30%, if you are a petrophysicist and using triple combo and using M equal to, you are going to recommend for your company, let's perforate this body. It have a good reservoir. It have a good saturation. But when I did reinterpretation and I used the previous cross plots that I shown to you by using triple combo, sonic, and the borehole image, I found that the saturation, it changed, it become 42, 45. So I compared this saturation with the irreducible water saturation obtained from the special core. I found it's 55. So I told the company, if you are going to perforate, I am predicting that you can have a combination of oil and water during production. You are not having a good reservoir quality. This is another story. The operator used M equal 2, but when I used the borehole image, I found we have a big fractures. So after doing the cross plot, I changed the saturation here. So the saturation first was around 75. So it wasn't perforated. After that, it was 55. So I recommended to the company, you may have a lot and to test this zone if you will have oil or not. For the NMR, because the NMR will be used in the next workshop, and the NMR is one of the most important tools for the acquisition for carbonate formation evaluation. We can see an actual example here for the application of the NMR. We see the porosity from the density here with the core porosity. We see the porosity from the NMR high resolution with the core porosity. We can see that there is a difference between the porosity from the density with the porosity from the core. The porosity of the density is higher, but the porosity of the NMR here matches the porosity of the core. And the reason of that, because this carbonate have some corrosion. So the corrosion will decrease the density log. And when it will decrease your density, it will increase your porosity. But the corrosion is a solid component. It's not a porous component. So the porosity of the density here was overestimated, but the porosity of the NMR here was correct. So we used the NMR porosity here for the volumetrics calculation. So you can see the application of the NMR in your porosity computation in the carbonate formation evaluation. It will not be affected by the corrosion, but the density was affected by the corrosion. And also, you can measure the Vuggy porosity of the NMR. Some studies from the core and the T2 distribution found any T2 distribution higher than 750 millisecond, it correlates with the presence of vugs in your reservoir. The last slide for our presentation today, as I said, that we are going to see the effect of the microfiches in your poroperm. We have here several points. You can do a linear trend for these different points. We see there are 2 points are highly correlatable. There is other 2 points here. I don't remember. The R square here was very good, also 0.9, and the R square here was also good. These reflect microfiches. Here reflect 2 microfiches. The connected vugs. Here is a vuggy connected by fractures and the intercrystalline pores. But this one and this one, I remember I didn't put their pictures. They were isolated vugs and they were a very low porous intercrystalline. So you need to correlate your poroperm plot with the texture of the reservoir that you have, because the microfiches is the main reason for your poroperm difference. You have for example, a high poroperm or you have a low poroperm. They will be correlatable with your microfiches, not lithofiches in the carbonate. I think I finished the presentation. and I'm expecting that we have a lot of questions. So let me check all the questions. Sorry. There are a lot of the chat. So let me go back. I'm checking from the first typing. Can we have, is there certificate? Why, the first question by Muhammad, why T2 is working in just water bearing zone? Let me go back to the NMR. It's a very good question. So when we are talking about NMR acquisition, when we measure the NMR, it's very simple. Its idea is very simple. I can summarize in 5 minutes. The NMR, it's based on producing a magnet in your tool and going down. So this magnet will, we have the magnet, and this magnet will polarize, which means, let me draw it for you to make it more understandable. Your hydrogens are randomly scattered. They are not oriented to the north. They are randomly scattered like this. So what will happen with the NMR? The NMR is going, by using its magnet, are going to polarize all these hydrogens into one magnetic field. So they will be oriented to one magnetic field called B node. And after orienting all the hydrogen into this B node, they all are aligned. Then we are going to do something called the transverse relaxation. We are going to align these hydrogens again to another magnetic field perpendicular to this magnetic field, 90 degree. So this 90-degree magnetic field is called B1. And then we are going to apply something called insulating magnetic field. What it means insulating, like you have, for example, from 0 here, sorry, and you have 90. The hydrogens will be like that, oriented in this from 0 to 90. Sorry, after they oriented from 0 to 90, they are affected by the three mechanisms. Something called surface relaxation, which is the interaction of the hydrogen with the grains. Bulk relaxation, which is the interaction of hydrogens together. Diffusion relaxation, which is related to the movement of the fluid from higher concentration to low concentration, which is always related to gas. So when you have a water, the water doesn't have bulk relaxation effect. The hydrogens are not interacted with each other. And the water doesn't have a diffusion effect. So they will be related to something called diffusion, to surface relaxation, which is the interaction of the hydrogen with the grains. And they found that surface relaxation reflect your pore size distribution. So in water-bearing reservoir, you can go to your T2 distribution and predict the porosity, if it's large pores or small pores. Okay, let me go up again because I see a lot of questions. I don't want to waste any questions from anyone. Oh, there is other question. Oh, yes. We can identify the fluid type with the NMR tool. Yes. It's based on something called the fluid mapping. The fluid mapping, let me draw for you. It's based on T2 here. Okay. And diffusion. And we have, for example, here line and here line. And we have here. This is the water. This is the gas. And this is the oil, if you have a heavy oil or light oil. And you can know the fluid type by each depth. It's called the station logging. Station logging. So you need first to understand the T2 distribution in details and diffusion in details. So it's a long story, but by using the fluid mapping, based on the cross plot between diffusion and T2, you can predict your fluid type. And there are surface companies now providing a high advanced fluid typing tool from the NMR. They can provide you a different fluid type with different depths of investigation. We can have this cross plot at 1 inch 1.5 inch and 2 inch and 3 inch. For example, tool like this called MR scanner based on something called shells. You can know the fluid in your formation after 1 inch, 2 inch, and 3 inch. It's called radial profiling fluid type. Let's check the other questions. We are going to share the presentation, don't worry. User certificates. What is the data acquisition program required for Clastic and the Carbonate reservoir characterization? This is very good question. Very, very good. Let me go here. Okay. If you are talking about Clastic, you can use density neutron, core, and NMR. Sonic is not important in the Clastic reservoir. You can use it only in 1 or 2 ways. But why I mentioned also NMR for Clastic? Because the shaly sand and the seam beds is much need the NMR, because the NMR can provide you something called bimodal distribution. The bimodal distribution is always present in the laminated reservoir or shaly sand. So the NMR is also essential in any shaly sand. But here you can use density neutron PEF. Spectroscopy is not important much in the Clastic reservoirs, unless if you have a water bismuth and you have, for example, let me give you something challenging in the Clastic reservoir. What if you have an oil bismuth and you have a gas unconsolidated shaly sand? A gas unconsolidated shaly sand with oil bismuth. Here you need a spectroscopy. Why? Because the volume of shale from the density neutron will not be trusted, because you are not sure that the hydrocarbon correction you did for the neutron density is correct or not. And they are not sure about the visual from the gamma ray, because maybe you have some radioactivity. So what is the optimum source of the volume of shale here? Spectroscopy. So the Clastic also sometimes requires spectroscopy, but for carbonate, it requires more spectroscopy. Also for image is essential if you need to know the paleo current, but it's not petrophysics, it's a geology port. Also NMR for the porosity, for the Clastic, and also for carbonate. So the Clastic is similar to carbonate, but it requires less acquisition of tools. Like you don't need much sonic here. You don't need spectroscopy unless the case that I mentioned. You don't need much thin sections and sonic. Even image only for geology. Here for sonic is not required for rock typing. Here also the dielectric only is applicable if you have a shaly freshwater sand. So we can see the carbonate require more acquisition of advanced tools compared with Clastics. Okay, let me go to other slide, other question, sorry. Okay, the other question is fracture density equal fracture intensity? Yes. Fracture intensity, how many fractures you have per 1 foot? Anyone expert in CMG? Are you meaning CPMG of the NMR? I don't know what you mean by CMG. If you can write it, I will answer you. But the dielectric tool assume M equal N. Yes, very good. This is the problem of dielectric. So what you are going to do, you are going to go to water bearing, because the water bearing carbonate, the N will be equal to, because there is no effective wettability. So you can take the M from the dielectric in the water bearing reservoir, and you can correlate by using the rock fabric in the remaining wells. Why high uranium is indication on fractures? Because the uranium is always deposited in the fractures because of the relation of the solubility of the uranium in water, and the fractures always has oil and water, so uranium will be deposited in the fractures. In a slide 17, M equal 1.7 used instead of M equal 2.4 because of the fracture at one depth. No, not what depth, it was this M is average. I wrote the average M value, but I used depth by depth this cross plot, and the M was ranging from 1.6 to 1.8. Okay. Does the NMR give total or effective? It provides both. NMR can provide total and it can provide effective. And also it provides an accurate volume of shale. This is the best part about NMR tool. I will share the presentation, don't worry. Okay, don't worry, I will share the presentation. Is the water contact in carbonate reservoir determined in the same way as the clastic? Yes, you need MDT points. But don't forget that the contact sometimes in the carbonate will be lower than the free water level if you have a strong oil wettability. Do we have a shelly carbonate like shelly sand? Yes, the micrite is considered to be a shelly carbonate, but it's a low resistivity carbonate due to the excess conductivity of the micrite. So you need to acquire sigma to have the water saturation from sigma, and you need to acquire the dielectric tool also to obtain the M and M, sorry, here. We will share the presentation. Do we get pore size? Yes, the pore size from the NMR, but the pore throat from the mercury injection. Take care of that. The mercury injection provide pore throat, but the NMR provide pore size in the water bearing. But there are high advanced technique now, something called NMR fluid substitution. You can remove the effect of the oil and you can estimate the pore size distribution from the NMR even if you have oil or gas. What is the rule that the capillary pressure of the carbonate? You must have a capillary pressure for the saturation height modeling because the saturation height modeling in the carbonate can provide a water saturation from the core and you can correlate with the logs. Okay, thank you, Muhammad. Thank you, Joanne. Thank you, Sumaya. So everyone, I think I finished the questions. If anyone want any questions, he can ask also in the group. I can answer. Please repeat how you calculate M. Okay, let me get back to the M. Let's go to the cross plot. Okay, so for example, you know that you have a Vuggy carbonate. You are going to determine the total porosity from the neutron density, and you are going to determine the porosity from sonic. And you see that you have isolated Vugs from the image. So at each depth, you are going to plot at each depth the value of the secondary porosity here and the value of total porosity here. You will go to the intersection point here and here and here, and at each depth you are going to have your M. Another method using water bearing carbonate. You are going to go to the water bearing, use the deep resistivity as R node in the FRF, use the RW from the salinity, and use log porosity. Then you can estimate M. Or if you need to pay, you can acquire dielectric tool, and the dielectric tool, the M will be equal N in the water bearing, so you will have an accurate M value in your reservoir. Okay. No, the free water level, you must have a free water level. Your questions that you mean that you didn't see the free water level. You didn't see the free water level, but it's always present. Can you first start the sliding that I missed? Okay, the first one, okay. Yes, the first one. Here I was comparing using triple combo alone with using NMR. Here I was talking that if you have a water-bearing carbonate, you have a low resistivity, but you have the gamma ray. The gamma ray is the same pattern and the density neutron is the same. But when we acquire the advanced tool like NMR, we found a deflection in the 2T2 distribution. And the T2 distribution in the water-bearing reservoir reflects the pore size. So when you have a high T2 as a time, it indicates larger pores. And you have a low T2, it indicates a smaller pores. Okay? So I think I answered all the questions, right? So I will stop share. And now reservoir solution, if you are with us, you
Okay,
can
thank you,
end the
Dr. Sama.
presentation.
Okay, thank you, Dr. Sama, for your great presentation. Actually, I think that all the participants benefited a lot of information that will add to their experience. So thank you again for your time and your effort.
Okay, anytime.
Thank you. Thank you.
Thank you.
Also, I would like to thank all the attendees for their attendance for our today webinar. Just I would like to remember them that if you wanted to engage into our upcoming integrated formation evaluation, in which we will have practical experience using datasets, real datasets to apply in software, you can enroll into the link that was sent into the Zoom chat. Also, in case that you wanted to have a certificate for attendance for this webinar, you can enroll into or you can fill into the form that sent into the Zoom chat. So thank you again and hope you good night, inshallah.